All right, so another example of I don't know, we've been doing conditional probabilities and we've been doing ands, which is kind of the multiplication rule. The probability that a randomly selected U.S. household has a cellular phone or landline is summarized in the table. So these are now probabilities instead of counts. Not that it really changes much, but it's a little different. So these are people that have cell phones and no cell phones, landlines and no landlines. And I think if we add up all four of these inside numbers, we would get our 100%. Okay? All right, calculate the probability that a randomly selected household with a landline will have a cell phone also. You really just need to read this a couple times and make sure you understand exactly what it's asking. Some people will think this is the probability of a landline and a cell phone, but it's not. Calculate the probability that a randomly selected household with a landline, so we're picking from people that have a landline, calculate the probability that they will have a cell phone. This is a probability that you have a cell phone given you have a landline. You have to recognize that as a conditional probability. If you don't, I don't see any way that you're going to get this right. All right, so given you have a landline, so this is one of those ones where we could kind of just look at this cell here if we wanted to kind of do it by our intuition, or we could fall back on the formula if you wanted to go that route. I really don't care which way you do it. I'm just going to do this one intuitively. What's the probability that you have a cell phone? 0.51 out of all the people that have landlines, which is 0.60. That's it. 0.51 divided by 0.60 is 0.85. The people that have landlines, of the people that have landlines, 85% of them also have a cell phone. I don't know. If I was in class, I'd ask you guys, do you want me to do it the other way? To do it the other way, I am going to do it the other way using the formula. The conditional formula is the probability that you have a cell phone and a landline divided by the probability you have a landline. So what percentage of people have a cell phone and a landline? That's 0.51. Divided by what percentage of people have okay, I guess I kind of didn't realize that was going to work out exactly the same way, but in this case it kind of did. So, alright, so I guess it doesn't matter which way you look at it. Tree diagrams. A tree diagram is kind of like a Venn diagram. It helps us, it's a useful way for organizing given information to help us find desired probabilities. But it's another thing on there. So now we got Venn diagrams, we got tree diagrams, we got formulas, we got intuition. I think this is why probability gets to be a little bit tricky, is that there's so many ways that you can go. And usually a given problem will have one way that's best. But you got to find it. But sometimes there's more than one way you can do it too. Chris Hale hits snooze on her alarm clock 60% of school days. If she doesn't hit the snooze bar, there's a 90% chance she'll make it to class on time. However, if she hits the snooze bar, there's only a 70% chance she makes it to school on time. Okay, makes sense. If she hits her snooze, she's less likely to make it to school on time. All right. List the given probabilities in proper math notation. All right, so she hits her snooze 60%. So the probability she hits her snooze is 60%. If she doesn't hit her snooze bar, there's a 90% chance she makes it to school on time. So that's not the probability she makes it to class on time. That's the probability she makes it to class on time given she doesn't hit the snooze bar. So the probability she's on time given she doesn't hit the snooze is 90%. And if she does hit the snooze, there's only 70% she makes. So this is a probability she's on time given she hits the snooze. So those are my probabilities that they gave us. Draw a tree diagram to describe this situation. So the way tree diagrams work is you kind of break it down by one event. It could be on time or not on time, or it could be you hit your snooze or you don't hit your snooze. So there's kind of two different ways that you can do it. But notice, I do know the probability that she hits her snooze. I don't know the probability she makes it to class on time because they never gave me those. So you kind of break it down by the probabilities that you have initially. So this is going to be snooze. This is going to be no snooze. And I know both of these probabilities. The probability that she hits the snooze is 60%, and that she doesn't hit the snooze is 40%. So we kind of put the events at the end of the bars, or the leaves, or whatever you want to call them, and the probabilities along the leaves. Now, if she hits the snooze, there's two possibilities. This is the second event. Either she's on time, let's say OT, on time, or she's not on time. And then if she doesn't hit the snooze, she's either on time or she's not on time. And I know these probabilities as well. This right here is the probability she's on time given she hits the snooze. So this tree diagram was made for these conditional probabilities here, which is why it's kind of nice. So the probability she's on time given that she hits the snooze is 70%. And if there's a 70% chance she's on time when she hits the snooze, then there is a 30% chance that she's not going to be on time if she hits the snooze, that she's going to be late. This is on time given she doesn't hit the snooze. On time given she doesn't. That's 90%. Usually she'll be on time. However, there still is a 10% chance that she'll be late. So because these are conditional probabilities, and this is the original hitting the snooze, basically it breaks this down into these products. So like this is the multiplication rule. So if you take 0.6 times 0.7, this is a probability. 6 times 7 is, 42, I think. And then 6 times 0.3, 0.6 times 0.3 is 0.18. I'm better at that. 0.4 times 0.9, 0.36, and 0.4 times 0.1, 0.04. What this does, this tree diagram helps us set up these possibilities. And if you look at these are actually mutually exclusive events. In fact, this is our kind of like our sample space. If you add these up, this adds up to 40%, this adds up to 60%, this adds up to 100%. This represents you hit the snooze and you're on time. You hit the snooze and you're not on time. You don't hit the snooze and you're on time. You don't hit your snooze and you're not on time. So these are those probabilities. Okay? So it's a nice way to organize our information. I could point out to you, how much do I want to keep going? Yeah, let's go. I'm going to mention this as well, that if you wanted to, you could actually organize this information in a Venn diagram. However, it's easier to start with a tree diagram and then go to the Venn diagram. I actually would have had a hard time going to the Venn diagram right away. By the way, you really don't need to do a Venn diagram, but I just kind of want to illustrate it to you that there is a link between these. So let's say this is hitting this. Actually, you know what? I don't want to do this. I don't want to confuse the issue. This is kind of a tree diagram problem, so let's not do the Venn diagram. All right. Find the probability that Chris Hill makes it to class on time. What's the probability that they make it on time? Notice this is not a conditional probability or an and. It's just what's the probability they make it on time. Well, there's two possibilities on how they can make it to school on time. She can hit the snooze and be on time, which is this, or she can not hit the snooze and be on time as that. But because those are mutually exclusive, you can just add them up. It is simply 0.42. I don't like that gold on there. It is 0.42 plus 0.36, which is 0.78. So there's, she's going to make it to class on time 78% of the time. What's the probability that Chris Hale is late? Well, sorry. Late would be not on time, not on time. Probability she's not on time equals 0.18 plus 0.04, which gives us a 22% chance. Dang it, I didn't really need to do this, did I? If there's a 78% chance she's on time, then there must be a 22% chance she's not on time. I could have used the rule of complements there. That would have been easier. And find the probability that Chris Hill hits the snooze if she is late for class. Okay, so find the probability that Chris Hill hit the snooze if she's late for class. Find the probability she hits the snooze given she's late for class. So I want the probability she hits snooze given she's late for class. This is a probability that she hit snooze given she was not on time. Sometimes this is called reversing the conditions. Notice how these were conditions the other way, and here they want me to reverse the conditions. So usually when you see that, tree diagram's your go-to technique. So this is, I'm going to go to the formula here because I can't really see it very easily. This is a probability that she hits snooze and she's not on time, divided by the probability she's not on time. So snooze and not on time. That's snooze and not on time. That's this right here. That's the 0.18. Over the probability she's on time. Well, not on time. Not on time is this one and this one. So that's the 0.18 plus the 0.04. So that is 0.18 divided by 0.22. 0.18 over 0.22 is 82%. 818. 0.818. So if she's not on time, there is a 82% chance that she hit the snooze. So these are pretty complex probabilities, in my opinion anyway. And if you're not careful, if you don't have a plan, if you don't do a tree diagram, if you don't organize your information, if you don't carefully think about what probabilities are given, I'm not so sure that people can just look at these three numbers and know how to do all of this stuff. But if you use your tools, you set them up and you take your time and you practice them, these are pretty manageable. Okay?